Hello and welcome to chapter 5. So this is going to be lecture A, and I'm going to make one more video with lecture B. All right, let's get started. Let's go over our learning objectives real quick. So today we're going to talk about cutoffs for normal and abnormal tests. How do we determine those? As we're going to see, it's not a very easy thing to do. We're going to talk about the validity in regards to testing or screening. So it will be a little bit different than what it is, what you learn in your stats class, essentially. We're going to learn how to set up a 2x2 table for screening testing results. We're going to talk about the true positives, false negatives, true negatives, false positives, and so on, and the gold standard. We're going to learn how to calculate sensitivity and specificity for a test. Essentially, we're going to learn how to evaluate if a test is valid or not. Okay, so without further delay, let's get started. In the previous lecture, we discussed the importance of early screening and how it helps us obtain incidence data by identifying new cases of disease. Deciding who has the disease and who doesn't is not an easy or foolproof task. There are several screening and diagnostic tests, some very expensive, others invasive, and others quick but not as accurate. To make matters even more complex, there are huge differences among individuals, and test results can be affected greatly by those individual differences. Disease detection is the foundation for secondary prevention. Remember that secondary prevention involves identifying people who a disease process has already begun, but I'm emphasizing the word "but" here. They have not yet developed clinical signs. We talk about routine testing. If an individual feels or shows signs that moves him/her to the tertiary prevention. So what is a normal test? How do we classify a test as normal? And when do we describe people who tested negative as healthy versus abnormal when people test positive? Well, the threshold for every test differs, as what is normal for a diabetes screening test may differ from a diabetes diagnostic test. The best case scenario for separating normal results from abnormal results would be when we observe a bimodal distribution. Remember here, bimodal means having two modes, two more frequent values, right? In this example, we clearly see the difference in duration diameters measured in millimeters for the tuberculin test. In other words, when you go in to get a tuberculosis test, the nurse tells you to come back in a few days to measure the induration in your arm. If you're negative, then the induration would be less than 3 millimeters. As you can see here from the bimodal distribution on the graph, and if you test positive, your induration can be as large as 20 centimeters or even greater. Consequently, that is pretty easy to screen. Unfortunately, not all diseases follow a bimodal distribution. So you can see right here, you're having this clear gap. So if you're falling in this side, you're considered healthy. And I guess if your induration is larger, you will be considered as, being positive, right? So this is a clear-cut case scenario. This is a unimodal distribution. And as you can see, it is continuous. Blood pressure can vary greatly among individuals. So where do we stop and how do we decide that from that point on an individual will be considered positive or negative, considering that the blood pressure is only one indication for overall cardiovascular health? For both distributions, either bimodal and unimodal, it is easy to differentiate among extreme values, people who are on either side of the distribution. It is the in-between cases that leaves room for interpretation and uncertainty, especially for the unimodal. So you can see, like, if you're falling in this extreme, you're probably negative, right? If you're falling on this extreme, we know that you're going to be positive. But what happens in this in-between values when we're actually having a unimodal distribution? Does that mean that if you're like at 130, you're kind of on the positive side, or are you healthy with a little bit raised blood pressure? You can see it's a very hard thing to actually set the standard. Screening tests differ from diagnostic tests because they're usually cheaper and less invasive. Screening tests detect potential disorders or diseases in people who do not have any symptoms of disease yet. The idea is to quickly screen people and, if test positive, to send them back for more advanced diagnostic tests. Now you're probably thinking that, is it a good idea to screen people with a test that may not be the most sensitive to capture all people who are truly positive? Well, since we're dealing with a large number of people, the initial screening test has to be affordable and quick. Of course, that will depend for what we're screening as well. A colonoscopy screening is not cheap test, and it's not, and it is definitely invasive. Quite a few men object the very idea, and they will decline screening because it is against their values. Unfortunately, a colonoscopy can save lives, and it's one of the only screening tests that will accurately detect colon cancer or other abnormalities within the colon. A fecal cold blood test is another screening test ordered frequently, but if positive, the person still has to go for colonoscopy. Colonoscopy, though, is not for the masses or for all age groups. It is usually recommended for people over the age of 50 unless they have a family history, which means they will start the screening earlier. Screening tests are not considered diagnostic, but used to identify a subset of the population who should have additional testing to determine the presence or absence of disease. The goal is early detection and lifestyle changes or surveillance to reduce the risk of disease or to detect it early enough to treat it the most effective way. In this slide, you can see side by side the differences between screening tests and diagnostic tests. I would definitely recommend you that you look this slide so you can really understand the differences between the two. In epidemiology, we have two ways of evaluating screening of a diagnostic test: sensitivity and specificity. Our aim always is to have a valid test, meaning a test that will truly distinguish between who has and who does not have the disease. Sensitivity measures the ability of a test to identify how well a test identifies those who truly have the disease. Specificity, it is the exact opposite. It tells us how well a test identifies those who do not have the disease. Now, if you remember from your Health Science 349 statistics class, we want to test to be both valid and reliable. Validity, to remind you, is how well a test does or measure what it's supposed to, and reliability is how well it measures and produces the same results over and over. Just like when you buy tires for your car, you don't want to buy them for a week. You want them to buy reliably, take them, everywhere and have them for several years. Likewise, a test needs to always perform well and not get different results every single time you run it. In a perfect world, there would be no errors. Everything would run smoothly time after time. In reality, though, a lot of things can go wrong, so it is crucial that persons who administer the test properly prepare patients and remain unbiased. As you can see in your slides, there are two types of error: random and systematic. Random is due to chance and not intentional by any means. For example, if you measure blood pressure in the morning, it may differ from late afternoon. If the individual had a stressful day or drank plenty of coffee, his numbers will be affected as well. That does not mean that the test is not accurate, and it does not mean that the individual has hypertension if he tests above the threshold. It is simply variation over time. Systematic, on the other hand, can be due to many things. It can be due to bias or even instrument error. Maybe one of the machines is not well calibrated and everything is a few degrees off. Regardless, our goal should always be to minimize error. This is a very important slide, and you should become very familiar with all those terms. A true positive refers to a test that is positive and the actual person is truly positive for the disease we're screening. A false positive is a positive test result, but the actual person is negative, meaning he does not have the disease, but his or her test turned out to be positive for some reason. A true negative is a test that is negative and the person is free of disease as well. A false negative is a negative test result, but the person actually has the disease and somehow the test failed to capture it. This is how we set up a 2x2 table in epidemiology. On the left, you will have the test results. So you can see you're going to put always your test results on the left side, and you're always going to put the positive on top and the negative. So this way you're going to be reading your test results. And then on the very top, you're going to have your disease status, okay? So that means, is the person actually positive for the disease? Okay, so pluses, they're going to go this way, okay? And then negative for disease. So anything that you're looking down this way, that means that the persons are positive for the disease, okay? Looking this way, the disease, the actual disease status is negative. So this is the actual status of the people. Going this way, you're looking at the status of the test. So you actually send people for testing, and this is how they test it, right? So you're either going to get true positives or false positives, but regardless, this is going to be all positive test results, and these are going to be all negative test results. In order to evaluate the validity or a screening of a diagnostic test, a gold standard for diagnosis is required. Gold standards are definitive and often highly invasive. For assessing validity, individuals must be administered both the gold standard and screening test. Now, as we previously stated, the goal is to minimize error, but having 0 false positive and 0 false negative is impossible. That is why we calculate sensitivity and specificity to evaluate validity. Here you can see that after having a screening or diagnostic test, this is what we're left with. People will either test positive or test negative. The question is how well the test accurately captures the true cases of disease, or what % of people are disease-free. Here are the formulas for calculating sensitivity and specificity of a test. For sensitivity, people who truly have the disease and test positive equals true positive divided by true positives plus false negatives. And we always multiply by 100 to turn it to a %. For specificity, okay, people who truly do not have the disease and test negative, right, it is equal to the true negatives divided by the true negatives plus the false positives multiplied by 100, okay? Because we always want to turn those into %. Now let's see an example and try to make sense of those two terms. Read the description that you see right here. And let's go ahead and draw a 2x2 table and start filling out what we know. So here it says you have a population of 1,000, of whom 100 truly have the disease and 900 truly do not have the disease. So that refers to your disease status. We want to use a test to distinguish those who have the disease from those who do not. The test correctly identified 80 people as having the disease, so that's going to be your true positives, right? The test correctly identified 800 people as not having your disease. That's going to be your true negatives. And so let's go ahead and fill out that table. And you can see this is what we know so far, right? So this is what the true is. You have 1,000 people, and out of the 1,000 people, 100 you know that their disease status is positive, and 900 people do not have the disease. Now, based on the description that I gave you, you saw that 80 people tested positive for the disease, right? Although you know that 100 are positive, but once you gave them the test, 80, you got 80 true positives and you got 80 true negatives, right? Once you know this information, you can pretty much fill out the remaining of the box. All you're going to have to do is subtract. So if 100 people have the disease and you got 80 out of them, right? That means you're going to have 20 false negatives right here, right? So these are people who actually have the disease, but for whatever reason did not test positive. Likewise here, right? 900 minus 800, you're going to have 100 up here. And these are false positives. So these are people who actually tested positive, but they're actually free of the disease. And this is how it's going to look, the finished table. Okay. Hopefully this is pretty straightforward to you. And you can see that we always notice that we calculate totals this way, right? So you have positive test results, 180 total, negative test results, 820 total, right? So again, 1,000 is always going to be 1,000 here, regardless which way you add your results, because 100 and 900, that's going to be 1,000 also, because essentially this way you're looking at the disease status, the true disease status, and this way you're going to be looking at what the actually test results were. Okay. So the disease status, you know that you have 100 people with disease and you have 900 people without the disease. So essentially you end up with 1,000, right? So it's always going to be the same. All right, so here you're actually doing the calculations for sensitivity and specificity. You simply follow the formula, right? So you got your true positives here, right? A, B, C, D, if you want to memorize it this way, whatever works for you. But essentially, this is your true positives right here, and this is your false negatives. The way that I like to remember sensitivity and specificity is that I'm going down this way when I'm calculating, because we're going to learn another measure in the next lecture that you're actually going this way. But for sensitivity and specificity, we're kind of like going down this way, meaning true positives up here, right? And then in your denominator, you have true positives again, plus the false negatives, right? So you see you're going this way. And then you multiply with 100. So you have 80 divided by 80 plus 20, that's 100, right? Multiplied by 100 also turn to percent. You end up with 80% sensitivity. Likewise, you do the true negatives, which is the 800 here, plus true negatives and false positives, which are those up here. And once you calculate those, you're going to end up with a sensitivity with an 89%. Have you ever wondered how we set those thresholds for disease status that we were talking before? How do we decide at what number someone will test positive or negative? One thing you need to know that standards do change over time. But let's closely examine a disease that a lot of Americans are affected, diabetes, and screening blood glucose levels. The very first graph depicts the distribution of blood sugar levels in hospital patients without diabetes. Okay, so this is it, the top one. And then the shorter, wider distribution right here in the bottom shows people with diabetes. Let's assume that we want to screen for diabetes and correctly identify those who are diabetes 100% accurately, meaning capture every single case who is truly positive. We can set the threshold at 8 mgs per milliliter, as you can see in the middle diagram, right? The problem is that we may capture every diabetic, but we also going to misdiagnose a lot of people who do not have diabetes but test positive. So you can see here, we can set our threshold really low, believing that this is the best way possible to capture every diabetic, right? Because you can see these are actually people who are diabetics. You know, so these are, I guess, diabetics, but with a low threshold, right? So we set our threshold right here very low to capture every single body. But now look what happens to the people actually who are diabetes free, right? We're going to get a lot of false positive test results. Let's go ahead and calculate the sensitivity, right? So the sensitivity here would be 28 divided by 28 plus 0, because we set it up at 100% sensitive, right? But specificity, right? It's going to be 39 divided by 181 plus 39, 17.7, okay? Now, you can actually view the actual 2x2 table in your text page. That's going to be, I believe, page 93, okay? So what I want you to understand here is that the more sensitive the test becomes, the more false positives we will have. And that is not good either. How would you like it if you went to the doctor, had a routine screening test, and then you get a call that you're positive, only to have to wait a few weeks to run a different test to find out that you're actually negative, right? So we do not want that. Now, let's go ahead and do the opposite now. In this figure C, we're going to set our threshold too high at 200 mgs per milliliter. Now, the problem is that we will miss a lot of true positive cases. So that is not a great idea either, because what you end up doing is you're going to send people home thinking that they're not positive, and as a consequence, they won't be getting the treatment they need. The specificity here is set to 100%. Remember, specificity is we really want to know who does not have the disease, right? So we're aiming for being 100% specific here, not sensitive, but specific. But that actually, what we'll end up doing is reducing our sensitivity. So we're going to miss a lot of people. Here you can see that the cutoff you select will greatly influence your test results. It is very difficult to select that perfect cutoff where you will have a very high sensitivity and a very high specificity. In other words, there's a trade-off between sensitivity and specificity, since we cannot have both at 100%. How do we choose? Well, it depends on the disease. Is the disease too deadly? And does delaying the treatment would have any immediate effects? Is the cost too high for a very sensitive test that would require further diagnostic testing? There are a lot of factors that will influence the decision as to where the cutoff is set. Let's explore now the issues that we will have to deal with if we make our test too sensitive, meaning too many people will test positive. Everyone who tested positive will have to come back and get additional, more expensive and sophisticated testing. Spending too much on unnecessary tests is not wise, since it would greatly increase the cost of healthcare. Furthermore, subjecting people to additional tests means days lost at work, unnecessary stress, and possible stigma from a false diagnosis. On the other hand, if we aim to not have many false positive and set specificity to 100%, then we may be sending home people who actually need treatment. Hence, selecting the appropriate level is very challenging indeed, and it varies by disease severity. All right, so this is our lecture for today. Tune in for part B. All right, take care.